Hello everyone, I'm Bin Tian. Today I have the privilege of presenting the research titled Fast Inference for Probabilistic Graphical Models. Unfortunately, the authors of this paper couldn't join us today, so I will be sharing the insights on their behalf. This is the outline of the presentation. Firstly, I will briefly talk about the background and motivation. Probabilistic graphical models can be described as a graph and parameters. In the graph, the nodes means random variables, and the edges means the relationship between variables. For example, Bayesian networks are a table of PGMs and are represented as direct graphs. As shown in the left figure, we can see a direct edge from difficulty to grade, which means the difficulty of the class can influence a student's grade. Markable random fields are another table of PGMs represented as undirected graphs. So they denote mutual relationships between variables. And the parameters qualify the strength of these relationships for the discrete variables. The parameters can be viewed as a set of tables. For example, in BNS, each node has a conditional probability table. The joint distribution can be decomposed into these small CPTs. For simplicity, we focus on BNS as examples of PGMs in this presentation, while we provide a unified perspective on BNS and MRFS in our paper. So PGMs use a transparent and intuitive graphical representation, and at the same time offer solid theoretical foundations. So they are attractive and have many applications. Inference is a crucial task on PGMs. Given a PGM, we often have some evidence variables. Inference is to calculate the posterior probability distribution of the core variables given evidence. For example, suppose we know that the course is hard and the student is intelligent, and we want to know quality of the professor's recommendation letter. Thus, inference is to compute the distribution over LTR given the evidence of DIF equals D1, ITN equals I1. Inference modes include extract and approximity modes. Approximity modes takes less time than extract modes at the cost of accuracy. So they are useful for applications where minor sacrifice in accuracy is acceptable. Importance sampling-based modes are a popular subclass of approximity modes. They use importance function to generate samples and estimate the probability from the frequency of occurrence in the sample. The importance function here is a probability distribution and can be decomposed into the importance CPTs of variables. This table of modes is the main focus of the work. However, developing an efficient system for this algorithm is challenging. Firstly, the problem of approximate inference is NP hard, which means that they have high computational complexity. Secondly, the irregular nature of graphical structures and stochastic nature of sampling process introduce significant challenges in memory and computation. Finally, abstracting and integrating various algorithms into a unified system is difficult. To address these challenges, we provide a system for importance sampling-based inference called Fast PGM, and it is designed with two primary objectives: good generality and flexibility and high efficiency. Next, I will talk about the first objective. We identified the 4 crucial steps and developed the 4 corresponding modules. Different algorithms have different computations inside each module, but we found that all the important sampling-based algorithms follow this general framework. Here, I briefly describe this framework. In the beginning, the importance function is initialized in the first module. After that, we enter the main loop inside each iteration. A simple C is generated with its importance source according to the PGM and the importance function. Then the source of each new sample is accumulated. During this process, the main loop is divided into multiple stages by the importance function update mode. The importance function is updated every 1 iterations, each update corresponding to a new stage. Symbol generation is the most important module. It gradually picks a value for each variable to form a symbol. In Bn, the variable handling order is topological order. And there are 4 steps for variable. Firstly, we get the instantiation of VG's parents according to topological order. The pairs of VG are always symboled before symboling VG itself. Secondly, we get a with vector containing the probability of VG's possible states based on the ICPT of VG and the instantiation of its parents. Thirdly, we randomly pick a value, and finally, the source of VG is computed and multiplied into the important source of sample. For example, suppose the INT is the evidence variables that equals I1, and suppose that the ICPT of each variable is a CPT. So first, for difficulty, the weight vector is this. We may pick D0 or D1, and suppose here we pick D0. Most algorithms directly instantiate the evidence variables as its observed state. So we have I1. Next, for grade, since we already get D0 and I1, we can get the weight vector, and we pick G1. For SAT, suppose we pick S1. Next, for later, we pick I1. Finally, we get one sample. We repeat this process, and we get many samples. Through our observations, we developed a unified framework for sampling-based proximity inference. Our fast PGM takes the PGM and the evidence as input, and outputs the posterior distribution of all the non-evidence variables using one of the supported algorithms. The first feature is versatile modules and functionality support. Since there are differences inside each module among different algorithms, we support various functionality. So different algorithms can use different functionalities, as shown in different color in the figure. Another feature is the quick new algorithm implementation. We provide the abstract functionality, and the red boxes show the default implementations of the abstract functions. The underlying data structure and the inference are also well implemented. So implementing new algorithms under our framework is quick. For example, implementing AI SBN based on fast PGM only needs less than 20 lines of code, but implementing it from structure needs at least 400 lines. Besides generality and flexibility, our second objective is high efficiency. I will talk about it from 3 steps. So the first one is memory management. Recall that the computations of the algorithms are based on the importance function, and recall that here the importance function is a probability distribution and can be decomposed into local ICPTs. So actually, the computations are through maintaining an ICPT of each variable. However, one challenge is the large memory requirement for storing these ICPTs. For example, for variable later that has a pyramid grid, its ICPT is like this. We can think of the ICPT as a map. The key is the state configuration of related variables, and the value is the probability. Since the later has 2 possible states and the grid has 3 possible states, the number of entrants is 6. In this example, the variable only have 1 parent, and the states of the related variables are small. But for highly contact complex problem, the variables may have many parents and many states, which cause many entrants in ICPTs. For each entrant, we need to store the configuration and probabilities. So this case a large memory requirement. To address this issue, our basic data structure uses a compact probability table structure to avoid storing the state configurations. It only stores the probabilities, and the corresponding configuration can be easily transformed from one table index through a hyperarray SUMST that stores the cumulative number of states. Another challenge is irregular memory access. The sampling process introduced unavoidable irregular memory accesses of ICPT and CPT. We found that ICPT and CPT for the same variable have the same structure, and the probabilities at the same position of them are frequently accessed together. So we improve the basic data structure by fusing the ICPT and CPT of each variable. In this way, if we access a certain probability in the ICPT, the related probability in the CPT is rarely available in contiguous memory location, which enhances data locality. It is known that the graphical structure can also cause irregular accesses to the node in the graph. Recall that we need to access the parents, so when handling one variable, so our goal is to maximize the proximity of each variable's parents. We propose a simple data reordering strategy to achieve this goal, given a directed graph. It first reverses all the edges, then get the topological order based on BFS. Finally, get the reverse ordering. In this way, we can get a valid topological order of the graph, which can be used to handle the variables. Compared with the ordering obtained by traditional moves, our ordering allows the pyramids to be positioned as close as possible in memory, so it mitigates a irregular access issue as much as possible. Another important aspect of high efficiency objective is computation simplification. Here focuses the most expensive operation, which is to get the weight vector of the variables in simple generation. Recall that this is done by reducing the ICPT of each variable based on the instation of its parents. Here is the example. Suppose V1 have 3 possible states, while V0 and V2 have 2 possible states. So there are 12 entrants in V1's ICPT. Suppose we have already known the instation of V1's parameter is V0 equals 1, V2 equals 0, and we need to traverse the ICPT to find all entrants that satisfy the instation. The size of ICPT is equal to the number of states of variables and its parents. So is the exponential in the number of related variables. We can also compute the overall complexity. With our proposed data structure, we only need to first get the location of V1 and construct the 3 configures. Next, we can easily get the 3 indices and fetch the probabilities. But the efficiency can be further improved through table reorganization optimization. Building on the basic data structure, we let the variable itself be on the rightmost position of the configuration. In this way, only the first configuration is required to be constructed. After obtaining its index, we can fetch probabilities from the contiguous memory. We also theoretically analyze the computational complexity. To summarize, our optimization significantly reduces the complexity and is particularly beneficial for complex graph with a large number of possible states for each variable. Finally, we use parallel techniques to improve the overall efficiency. The most natural scheme is to parallelize different test cases because the test cases are independent of each other. However, it may cause a lot of imbalancing issue because different test cases different evidence variables, which greatly influence the workloads. Another scheme is the variable-level parallelism, which parallels the simple process of different variables. However, this is parallelism which parallels. This is inherently sequential, so we need to first partition the graph into independent subgraphs. But not all graphs are easy to partition. Moreover, this parallelism has relatively small workload, which can amortize the parallel overhead. Therefore, we implement a simple but efficient simple level parallelism. Recall that the main loop of is divided into multiple stages, but the importance function update module. Different symbols generated inside the same stage use the same importance function, and the workloads are the same. So the algorithms are well suited for simple level parallelism. In this way, we can address the efficiency issue and adapt to various PGM structures. Next, we conduct extensive experiments, and I will show the key result here. We first compare fast PGM with 2 other implementations. We show that we support more algorithms. Fast PGM is 3 and 20 times faster than the SOTA implementation SMILE. When compared to BNG, fast PGM often achieves 3 orders of magnitude significant speedup. We also conduct experiments to investigate the impact of individual optimizations. Here, we briefly show the result on 2 algorithms. Overall, the 6th graph, 25% improvement is from memory management, 14% from computation simplification, or 61% from parallelism. We can also observe that learning-based algorithms benefit more from memory and computation optimization compared to no learning-based algorithms. We leave detailed discussion and analysis in our paper. Here we show the theoretical speedup computed by Adam's law and the practical speedup. We also show the ratio of sequential and parallel paths. We can observe that our practical speedup approaches the theoretical speedups. We also plot the accuracy result for the scale of completeness. In the fast PGM, we support the handler's distance and means squared error, which are well-known accuracy metrics. Generally, EPIS-BN is the best while PIS is the worst. The accuracy result from our implementation are consistent with that the previous paper. We leave future observations and analysis in our paper. Finally, I will conclude the paper. First, we propose fast PGM, a system for PGM inference. Through abstraction, fast PGM provides a general framework with rich interface, enabling fast and easy optimization, extension, and customization. Secondly, we incorporate memory management, computation simplification, and parallelism techniques, which are applicable to other PGM topics and can inspire acceleration for broader class of graph-based algorithms. Thirdly, we conduct experiments to study the effectiveness of fast FPGM and the impact of our optimizations. Future work could extend fast PGM to distribute the environment and incorporate additional inference algorithms. Thank you for listening. Since the author couldn't come to the scenes, if you have any question, you can contact the author through the email. Thank you.